It is my pleasure to introduce Professor Michael Dickey from North Carolina, Department of Chemical and Biomolecular Engineering. So I'm Petya Vlahowska, by the way, if you don't know me. I'm from the Engineering Science and Applied Math, and I've always been, I came across his work I'm not going to tell how many years ago, but there was this fantastic work on droplets of liquid metals and doing crazy things. And I'm very excited when I learned that he's going to be coming and giving us an update of where things are with all these soft, fascinating objects. So Michael did his PhD in Georgia Tech or undergraduate?
Georgia Tech.
Okay, maybe you should introduce yourself. And the PhD was University of Texas. Okay, so and then he spent some time as a postdoc in Harvard, and he's been traveling around the world. I just found out he was on sabbatical in EPFL a couple of years ago. And well, he's also now visiting us in Evanston at Northwestern to tell us a story about shaping a soft future. I am thrilled. Welcome, Michael.
Thank you. Thank you for the nice introduction. Yeah, I think the microphone's good, right? You're welcome. Thank you all for coming. I know there's free lunch, so that's already good. I'll try to entertain you while you eat. I'm really excited to be here. I've always wanted to come to Northwestern. It's actually my first time coming. It was a little tricky because in Raleigh, when I left, it was about 75 degrees. And this is a little cold for my southern blood. So next time I come, I'm going to come a little bit later into the spring. But anyway, it's been really fun to visit. And let's see, go here. So in our group, we work on a number of different things that are united by the importance of these words: interfaces, patterning, soft materials. And those words are intentionally vague to kind of capture some of the different things we do. So I'm going to show you one example. This is something I'm not going to talk about, so you'll just have to watch this video. But we do some work on polymers. And in this case, we've taken a polymer sheet and we've patterned it with black ink, which you can see here. And when we shine light on this material, we take a two-dimensional shape and make it three. Thank you. Good reaction. I can always tell if people react like this is going to be a good talk or bad talk. So I need this. Please give it to me. Okay. So anyway, the idea here is that there's a lot of different ways to pattern things in 2D. So like inkjet printing, the way that transistors are made, these are all two-dimensional processes. So we were trying to take those types of processes and make 3D shapes. If you're curious, I'll tell you more about this maybe at the end. So that's what I'm not going to talk about. What I'm going to start talking about is work on liquid metals. And the motivation here is sort of captured in the title of my talk, which is the soft future. And what do I mean by that? Most devices that we have these days, whether it be your cell phone or your computer, or if you're really sophisticated, maybe a robot, they tend to be made out of rigid materials. Yet our bodies, other than bones in our bodies, are mostly made out of soft materials, and they can do very sophisticated things. So we're interested in trying to, make devices and materials and stuff that can be worn on the body, in the body, maybe even in like clothing, that sort of thing. And in particular, we're interested in electronics. So, if you think about materials, this is sort of this whole spectrum of different material mechanical properties. So this is Young's modulus, which is a measure of how hard a material is. If you go way over here on the right-hand side, you'll see diamond, which of course is very hard. If you go 1,000,000 times softer than that, you get down into rubber, which of course is stretchy and soft. 1,000 times softer than that is biology, like tissue, cells. And then way over here, you see liquid metals. And that's exciting because it means they're very, very soft, and they're metals, so they're also conductive. And so we have been basically working with liquid metals, and the first thing is, well, you got to choose a metal. And most people, when they think of liquid metals, they think of mercury, which is toxic. There's also these elements over here that are really nasty, but they have low melting points, so they're either explosive or radioactive. So we don't want to use those either, so I've colored them red. And so really by process of elimination, that leaves gallium. And gallium, you'll notice in the periodic table, is right below aluminum, which means they're kind of like brothers or sisters. They have very similar properties, and that's important. But there's one big difference that I'll tell you about in just a second. And so I thought I'd use this chance to mention I would feel a little self-conscious because I know this is an institute on complexity, and there's a lot of different disciplines here. And you know, I was asking myself, well, is what I do really complex? Well, this material, I would say yes, is complex, but it's not really a complex system. So thank you for coming despite despite that. But I will say, you know, again, to be provocative, is gallium the most interesting element? And well, I know you're eating, so I'm not going to ask you to answer, but the answer is yes. And now that I've put my neck out, I'll say I'm a little bit biased. So let me now try to convince you why this is so interesting. So remember, gallium and aluminum are like brothers. And so I see some of you, there's an aluminum can, an aluminum can. Of course, aluminum is solid, but gallium, despite having very similar properties to aluminum, if you hold a crystal of gallium, which is shown here, and you hold it in your hand, your body temperature is enough to melt it. We don't want to have to hold it in our hand to ensure that it's a liquid, so we add to the gallium, which is shown here, crystal of gallium, we add to it indium, and that depresses the melting point and makes it truly a liquid at room temperature. So a lot of what I'll show you today is either gallium or gallium-indium liquid metals. And I would like to tell you a little bit more about their properties. So one thing about gallium is it doesn't evaporate. So if some of you, I see you're drinking water, if you spilled a little droplet of water on this table, you might want to wipe it up just to be polite, but you could probably also leave it here, and probably within an hour it would be evaporated, right? That's because water has a vapor pressure, it vaporizes, no surprise. But gallium does not. It's 0.00000, basically zero. Okay, so you don't have to worry about breathing it, you don't have to worry about it going away. And people often say, well, oh, okay, this is really cool, but it's a liquid metal, it's got to be toxic. I would argue that toxicity has nothing to do with melting point, right? Otherwise, I mean, water has a low melting point. So gallium is not part of our natural diet. You all are eating sandwiches. It's not in your sandwich, and I don't encourage you to eat it. But if you did, the body has a way of dealing with it, and it's considered to have low toxicity. All right, so what else is interesting about it? Well, it's a liquid, and the viscosity is like water, and so as a consequence, you can simply dispense it from a syringe. So here we're just using our thumb to squish it out of a syringe, very much like water, but again, with metallic properties. And it's conductive like a metal. So this has a little bit of sound. I'm not sure if you'll be able to hear it or not, but there's liquid metal in this rubber tube. And what we've done here is made a wire that's as stretchable as the polymer that encases the liquid metal, but is conductive as a metal. So let's see if this plays sound. If not, it's okay. Should I unmute it just for a second? Nah. Okay. Well, if you could hear the sound, we're playing the NC State fight song, and you'd hear that there's no degradation in sound quality while we stretch these wires just like a rubber band. So you get the best combination of conductivity and stretchability. As far as I know, nobody has beaten this record. And we cut off one of the headphones so that all the sound came through here. Anyway, this video is on YouTube. You can check it out if you want to hear the volume, hear the sound. Okay, so we can make really soft, stretchy stuff. But the real key thing, and I hope that you're watching this because this is the key point, is that the metal forms an oxide on its surface. And this is not surprising at all because remember, aluminum, its brother or its sister, does exactly the same thing. Did you know that aluminum is extremely reactive? Very reactive, yet we have it in our kitchen. Why is that possible? Because on the surface of this metal, just like on the surface of the liquid metal, there's a very thin oxide layer that forms due to the reaction between this metal and the oxygen that's out in the air. And this does a few things, one of which is it protects it from additional oxidation. So it protects the metal. So if you have stainless steel, there's an oxide on the surface. Aluminum, an oxide on the surface of those cans of soda that you're drinking. So, well, why is this useful? If you want a metal, you don't really want an oxide. But this is particularly useful in this case, so please watch, because this is the liquid metal on a glass slide, and if we use a little bit of acid, it will dissolve away that oxide layer, and without the oxide skin, the metal just beads up due to surface tension. So, oh, by the way, gallium has the largest surface tension of any liquid at room temperature known to man. So another interesting thing about it. And so that's why it's beating up. But with the oxide, obviously we can spread it out like wet paint. So even though we've added indium to the metal, to the liquid metal, it's gallium that forms this oxide layer. This is gallium oxide. And it's passivating, which means it forms and it doesn't get thicker with time. Aluminum does the same thing. Okay, so why is this useful? Well, one thing it allows us to do is pattern liquids in ways that are not possible with water or coffee or tea or whatever. So here we're sucking the liquid metal back in. You can see the oxide wrinkle. And this oxide forms essentially instantly, very, very fast. And so as a consequence of this, remember, 3 nanometer thick skin that forms on the surface, we can take this liquid that's in many ways like water and start to make 3-dimensional shapes out of it. So here we're just taking droplets and stacking them. And at the time, this was the first example of printing metals at room temperature in really a very simple way. So here we stack droplets. You can also do a burst of pressure, and it will oxidize so fast in midair, it's a little like Spider-Man forming a fiber. But unlike Spider-Man, this is more like a garden hose where it's liquid on the inside, so you can drag it around and it's conductive. And then this is as close as we get to biology in my lab. This is a dead bug. Can you see the eyes? There's the eyes. Anyway, my student did this as a joke, but I really like it because it nicely shows how gentle and, this is a room temperature process, and yet how small these structures are. This is on the head of a bug. Okay, so that's one way to pattern the metal, but another way to pattern it is to simply inject it. So here we have what's called a microfluidic channel, which is just a tube, and we apply pressure right here, and we inject it, and it pops out on the other side. We're going to do it again from here through here. And so this is interesting because you can't do this with copper or aluminum or other common metals. And if you inject this into a piece of rubber, you end up with a rubbery like wire, which is what we've done on the right-hand side of the slide where we've made different types of antennas, like a bunny ear antenna. This is called a dipole antenna. This is on the top right. The middle one is a coil for wireless power transmission. And on the bottom, these are electrodes for microfluidic channels that we can make simply by injecting. So it's really, really easy fabrication. But it turns out it's even easier. I'm starting to feel like a car salesman, but wait, there's more. And that is in the previous video, if you imagine this to be your tube, and you're injecting this way, as you push the metal in, the air escapes through a hole at the outlet. In this video, there's no outlet. It's closed. There's only an inlet, and we put a droplet of the liquid metal on top of it. So it's a little bit like an ice cream cone where you've got the ice cream sitting here, and there's a little hole underneath it that's being covered by the liquid metal. We put this whole thing, this is a slab of silicone with microchannels, which you can faintly see. We put that into a vacuum, and we pull all the air out, which actually renders these channels under vacuum. And then one of the cool things with liquid metal, you can see the reflection of the student. This is when he was a grad student, now he's a professor. But anyway, you can see his reflection as he turns the valve to the chamber, which lets the air back in. And this will cause atmospheric pressure to push right here. And these are still under vacuum, and so it pushes the metal in. Very, very simple, hands-free fabrication. Okay, so what is this good for? Well, you can make stretchy stuff, but you can also address a long-standing trade-off in materials, which is if you have a material that is it's stretchable, like say a rubber band, it tends to have very high gas permeability. And well, why is that the case? I'm kind of a visual person, so I'm going to see if I can. But if you imagine you have a polymer chain like this. So you have a polymer chain that's coiled and it's stretchy. When you pull on it, it uncoils like this. And that's what makes like rubber stretchy, for example. But that very same thing that allows this chain to move allows gas molecules to zip right through. And so a lot of stretchy materials tend to be not very good barriers to gas. And so if you don't believe me, even plastics, like the plastics that are used in bags of potato chips, tend to have a metal liner inside of them because otherwise the potato chips would go bad either due to moisture or oxygen getting in there. And so you can imagine how we kind of break this trade-off. We combined liquid metal with rubber to make a hermetic seal that has low gas permeability but still stretchable and soft. Why would you do that? Well, one example is batteries. So batteries typically come in these rigid containers. That's to keep the liquid inside and also to keep the oxygen, which is reactive, on the outside to not let it come into the battery and destroy it. So we made one of these, and you can see a picture of it here. This shiny stuff here is our liquid metal coating, and you can see the electrodes of the battery here. And we measured the mass versus time. We're not the first people to make stretchable batteries, but the dirty little secret is in other batteries, over time they degrade because the liquids on the inside just diffuse out. But with ours, the liquid metal coating basically is a hermetic seal. In fact, we had trouble measuring the permeability because it was so low. It was below the level of the instrument. So it's a really good stretchable barrier. All right, so this is a part I'm really excited about. We just published this recently, but the reason I'm excited about this is I've dreamed about this for, you're gonna laugh, but probably 10 to 15 years. And that is to separate the oxide from the metal. And it sounds so simple, like you could just somehow pull it off. But before I get ahead of myself, this is what we're trying to do. Imagine having an apple where the skin is really valuable. Most kids don't like the skin, but in my case, I want the skin. I just want the skin and remove it from the metal. And why would you want to do this? Well, oxides are everywhere. They're in electronics. So if you have one of these, I think you do, oxides are in there, multiple places. They're in sensors. If you wear glasses or the glass on these windows have optical coatings made out of oxides. And then your touchscreen on your cell phone is indium tin oxide. It's a transparent conductive oxide. So they're everywhere. And the way that they're typically made is using what I call vacuum processing. So this is just an example, a picture I found from the internet where there's this glass tube. So suppose you wanted to deposit an oxide on this surface. You would put your object inside of this tube, pull all of the gas out, then heat it up, which is what's happening here. You can see it's glowing, and you flow in some reactive chemicals and it will deposit. So it's slow, it's expensive, it uses high temperatures, it uses vacuum. There's a bunch of things not to like about it, but it works. So that's something to like about it. All right, so let me explain why I've been dreaming this for 15 years and why it took us so long. So there's a report in the literature, and I won't say where it's coming from, but a report in the literature that says, if you just take your liquid metal, which is a little droplet here, and let's say you want to get the oxide onto this surface. Well, why don't you just touch it? This is called touch printing. You just touch it, and then you pull it off, and you should get just the oxide. And I don't know if you can see here, but there's not just the oxide, there's a bunch of metal residue. So I'm going to make a sad face because that's why for over a decade, we've not been able to do this. Okay. Well, maybe there's another way to do it. Maybe, remember this thing is kind of like a water bed where you've got the skin, you've got liquid on the inside. What if we just sort of like cut the bottom of this popsicle, drained all the liquid out, and then we'd be left with just the plastic, the skin, which is what we want. And that sounds like a good idea too. But let me show you. So here you take a puddle of liquid metal, and sorry for the video acting funky, but if you tilt it, you'll see that the liquid flows down the glass slide just as you would expect if you took a puddle of water and you tilted it. It would just flow down. But unlike water, the weird thing, and we don't understand this, is it forms a film. And this film is stable. That's weird because this has got a viscosity like water. It's got a surface tension that's enormous. It should not make a film. Now, obviously, the oxide's playing a role here, but what it's doing exactly, we don't know. So the popsicle analogy does not work. It's not easy just to remove the liquid. It tends to want to be inside of its own oxide. But turns out, if you take that same film and you scratch it, you can actually destabilize this film, and indeed, the liquid will flow. Good reaction, thank you. I had the same reaction, I almost fell over. So the liquid drains, and what's left behind is just the oxide. Okay, and so that's one way to do it, but it's not the best way. And so I'm telling you kind of the high-level version of this, but Woojin gets a lot of credit because he sort of figured this out. But the short version, without going into a lot of detail, is that the liquid metal inside of its own oxide actually has a very low surface tension. It really likes to be in contact with the interior of its own oxide until the contact angle that's formed right here gets low enough. And when it gets low enough, about below 20 degrees, it will spontaneously collapse. So it wants to be at around 20 degrees. So in the previous video, the liquid drained due to gravity, but I can show you where we've done this even on flat surfaces. So here's this black thing is the liquid metal, and you're seeing a reflection of it. So it's actually just a meniscus, and you're seeing the reflection. But anyway, after we've made this thing unstable, you'll see that it will collapse, and you can't see it because it's so thin, but this is the oxide. So it's just leaving a beautiful layer of oxide. And so there's even a kind of a better way to do this. which is to take the liquid metal and essentially drag it across the surface. So what we do is we put the liquid metal, we call it a printer head. That's a very fancy word for saying 2 glass slides that are like this. And we put the liquid metal between it. And this is not quite to scale. There's a small gap, maybe 500 microns, where we drag it. But the key idea is that when we drag it, this oxide layer, when you start moving this way, you basically mechanically make this angle small enough, and this will start collapsing. Now, there's also oxide on this leading edge, and so you actually end up getting 2 layers, which I'll tell you about in a second. So this is what it looks like. Minsik was a visiting scholar in my lab from Professor Zhang's group, and he really helped advance this in our group. So what you're going to see, it'll happen kind of quick, but you're looking from the side, and we're dragging this. Here's the meniscus of the liquid metal, and what's left behind is the oxide. Now, I know the box folding was cool and the vacuum filling was cool, but this is even more cool. It's just there's nothing to see. And that's what's so cool about it, is that the oxide that we're depositing is beautiful. There's no defects. It just completely covers this large area. And this is at room temperature. No vacuum processing, no high temperatures. We're depositing oxide. Now, there is a little bit of liquid residue at the edges, which we can't seem to quite avoid. But other than the edge, we're just depositing the oxide. So this just kind of summarizes what I've shown you, that we're taking the liquid metal between this little slot, dragging it across, and relying on oxidation to get this to form. And what's quite cool about this is that there's other metals like aluminum. Remember the brother, the sister? It dissolves a little bit into gallium, but aluminum is even more reactive than gallium. And so if you put in 1% aluminum, you can actually deposit aluminum oxide, which is crazy because aluminum melts at like 660 Celsius, and we can deposit it at room temperature. Okay, so I mentioned before that you have oxide on the leading edge and the trailing edge, and they collapse on each other, so you actually end up getting a bilayer. That bilayer is about 4 nanometers thick, which we've measured in a number of different ways. This is what it looks like. We've printed on all sorts of different substrates, PDMS, sapphire, which is kind of like an oxide, gold, different polymers. And you'll notice, I'm going to come back to this, but you notice this kind of grayish color. That turns out to be important. It's transparent, but it's gray. The oxide we deposit is amorphous, not surprising. Most native oxides, as far as I know, are amorphous. And even though we only get 4 nanometers with one pass, we can do multiple passes. We can print, print, print. And you can see there's some liquid metal residue, but when we wash that away, you're left with just the oxide. So we can control how thick this is. Now, the really surprising thing, I thought, okay, depositing oxides was cool, but if it's just an amorphous oxide, it's only got limited applications. But it turns out this film is quite conductive. That's weird. It's very, very weird. And so we think, I'm not going to show you all the evidence for it, but we basically think that there's a metallic-like layer in the middle. So remember where I said, remember it's gray? That's evidence that there's some metallic character to it. So if you measure the conductivity, I don't know if these numbers mean anything to you, but most metals are around here, 10 to the 6. So it's almost got metal-like conductivity. But unfortunately, if you look at the red data, which is where we've printed one of these bilayers, you'll see it's conductive, and then after about a few hours, it dies. And when it dies, it starts to become even more transparent. That gray color goes away. So it means whatever sort of metallic character this bilayer film has, it goes away, it oxidizes. So we said, well, okay, what if we print 3 layers? Maybe it'll sort of protect it, and it does, which is what this green data shows, but eventually even that starts to decay. So I don't love the solution I'm going to show you, but it ended up being very interesting in a kind of an unexpected way. So we took this bilayer film, and we put it in one of those chambers I described to you, and we deposited 4 nanometers. It's like nothing. It's like a little dusting of gold. So here come our gold atoms. We deposit on there. And it turns out that metal sort of gets incorporated into the film. We call it metal decorated. It's kind of a silly word, but so I need to give you a little bit of background about why this ends up being so interesting. So first of all, if you deposit 4 nanometers of gold on most surfaces, you end up with little islands of gold. These little white spots, this is from the literature. These little white spots are gold, and there's no way that this is going to be conductive, because if you try to apply electricity through this film, there's no percolated pathway. So that's bad news. And in fact, if you deposit 4 nanometers of gold on gallium oxide, you end up with little islands. And if you look from the side, you look at a side view, those little islands, they look like little dots. So that's gold, that's gold, that's gold, but they're not connected. So it's not going to be conductive. But on our printed oxide, we print it fresh and then we deposit gold. This is what it looks like. Not islands, it's uniform, it's transparent. You can see this is gallium oxide, the word gallium oxide printed on a piece of paper, put behind our film. It's transparent. But the main thing is compare the way the gold looks here, continuous film, versus there, little islands. Okay, so one thing, if you haven't done this before, one thing you may not appreciate is, let me go back. So I'm going to show you 2 things. First of all, this one's conductive, that's not. But also, these little gold things don't really have a strong bond to the surface, so they're very easy to remove. So I'm going to show you both of these results. First, when we add the gold, you might remember the red data is where we have one layer of oxide, but eventually oxidizes. If we add the gold, not only does the conductivity go up like a metal, but it becomes very stable, up to like 600 degrees Celsius. So it's a very stable conductor. And then, like I said, the surprising thing is gold. If you take gold and you deposit it on almost any surface, but especially oxides like, say, glass. So here's gold, here's our gold film on glass. This is a thicker layer, so it's actually a film. If you can just come with some glue, like epoxy, you can actually just rip that right off. I mean, ripping's even being generous. You can just easily peel it off. It's not stuck. So let me show you again why this is so kind of interesting. We deposited 4 nanometers gold on polyimide. This is a material used for flexible circuits. And so it's kind of got a yellowish color even before we put the gold on there. So here's our film. On the left-hand side, we deposit our oxide film, 4 nanometers of gallium oxide. And then over the entire sample, including where there's no oxide, we deposit the gold. And then we come in with a toothpick, and you can see it rubs right off of the polyimide, but it does not rub off of our film. So this is the only material I know of that gold sticks to other than other metals. Because gold can form metal-metal bonds, but it can't form good bonds with plastic or glass or other materials. And so this is a very simple way to make an adhesion layer for gold. And anyway, these films are very thin and transparent, so this feels like a trick out of John Rogers' playbook, who's traveling today, so I didn't get to see. But anyway, we transferred it to a leaf. You can see it's very transparent, it's conductive. And then we also put it onto a PET, which is, oh, my Coke bottle's over there. It's like a Coke bottle material, but very, very thin, so it's flexible. And so we were able to make circuits out of this. This is just as simple as you can imagine, just lighting up LEDs. But it's very durable, scratch resistant. You can flex it many, many times, and it doesn't fail. Okay. So one last thing I want to show you about liquid metal is I mentioned it has a very large surface tension. In fact, 10 times the surface tension of water. So if you put it in, this is in base, sodium hydroxide, so there's no oxide. If you shake this, it breaks up into droplets, just like salad dressing. But as you can see in the video, it very quickly goes back together. So this, does anybody know the surface tension of water? This might be helpful. I didn't get to teach spring break for us, so who said that? 72, A+, good job. You can go home. Oh no. Let's try red for NC State. There we go. All right, let's not worry about the units, but it's 72 millinewtons, which is a force per length meters. Okay, so this is about 600. So most liquids you encounter, like water, 70, oil is like 30. Maybe I should write that up there, but this is about the highest surface tension of any liquid you would encounter day to day. This is like 10 times bigger. Okay, so this was something we discovered kind of on accident, but it turned out to be very interesting. So this is this really large surface tension liquid in sodium hydroxide, so there's no oxide, and we stick an electrode into it and we apply a positive voltage, which means we're going to oxidize the surface. And what you would expect is just a shell of oxide to form on the surface and nothing should happen, right? I've already shown you we can 3D print the metal. Well, when we do this, we apply the voltage, and we apply it relative to a counter electrode, which you can see at the top of the screen. It spreads like a pancake. Remember, surface tension is 10 times out of water, which means it really wants to be a ball. Now you can see at the counter electrode, there's little bubbles forming. That's hydrogen that's being formed. So we're reducing water while we're oxidizing the liquid metal. Okay, so this is really weird, and you should be asking yourself why. Well, our first thought was maybe this is what's called electrocapillarity. This has been known since the 1800s. And so I need to kind of walk you through this, but this is a plot of surface tension on this axis, on the y-axis, and potential on this axis. And if you imagine you have a droplet of the metal sitting in electrolyte, it's got a very large surface tension. Remember water? 72? This is like 600. It's huge. Well, if you want to trick the metal into liking the water, one thing you can do is apply a potential to it. And if you apply a positive potential, you'll draw negative ions from the water. And if you apply a negative potential, you'll draw a positive. But it doesn't matter. Either way, it will lower the tension. So what does this look like in terms of a circuit element? Is it a resistor? Okay, good job. You can go home too. A+. Capacitor. And so the equation that describes this is the surface tension, which is what's being plotted, is equal to the surface tension at what's called the point of zero charge. Up here where there's no charge on it, that's the peak of the parabola, minus 1/2 CV squared, the equation for a capacitor. Voltage squared means it doesn't matter if you apply positive or negative. But I'd like you to point out to you that the change in tension shown here, it goes from 600 to 500. That's actually a big change. That's bigger than the entire surface tension of water. But still, at its minimum value, it's still 500, which is huge. That's bigger than mercury. So it will still form a droplet and not spread. You'll also notice, well, look at this equation. Shouldn't I just be able to apply any voltage and just keep lowering the tension, going on and on? So why did these people stop taking data? Here, why not apply a bigger voltage? Well, that's part of the reason. What happens when you apply a voltage in water? Yeah, hydrolysis. Man, A++. A new category. Thank you. Hydrolysis. These charges that you're applying start combining. You get what's called Faradaic reactions. You get bubbles. So over here, you'd get oxygen. Over there, you'd get hydrogen. So there's a limit to this effect. And so for a number of reasons, I just told you a whole story, and now I'm going to tell you it's not electrocapillarity. Because when we apply negative voltage, actually the metal beads up and we see bubbles form on the surface. But when we oxidize the metal, it spreads. So it's not electrocapillarity. And so we made our own electrocapillary curve. So we take a droplet of the metal and we stick a little electrode into the bottom so we can apply a voltage to it. And we are able to measure the surface tension based on the shape of the drop. So if the tension's really high, it will look round like you can see here. But as we start to lower the tension by applying the voltage, it will start to squish. And based on the shape, we can tease out the tension because we know the gravitational forces. Those are the only two forces. We know one of them. We can tease out the other one. So here's our experiment. Here's our droplet. You can't see the electrode, but it's sticking in here. There's a syringe there just for scale bar, but it's not doing anything. And somewhere in the solution, which you can't see, there's a reference electrode, counter electrode. I'm going to make that go away just so you can see the data. But one of the weird things about electrochemistry, when we just stick the electrodes in and we don't apply any voltage, we get what's called an open circuit potential. This is just like you stick two different metals. It's the potential between them, negative 1.5. So think of this like 0. We're not doing anything. And the tension is at about 500. What was the tension of water? 72. So pure water is down here. The liquid with the largest surface tension that you probably experience in your life is down here. So this is a huge tension. And so when we apply voltage, you'll start to see that the tension lowers, the droplet squishes, and then it goes even lower. So we apply more voltage, but it's completely reversible. And we can go back and forth. This is real time. It's very fast. And so we're getting absolutely enormous changes in surface tension by just applying a fraction of a volt. So, okay, so what's happening? Well, let me skip ahead. So if you take this data, and well, first of all, remember the theory predicts a parabola, like a capacitor. And so if you put some of our data on there, it follows the theory perfectly. It's acting like a capacitor. We're just putting charge at the interface. But as soon as we start to see oxidation, where you see electrochemical reactions occurring, we get this anomalous behavior and where it drops very, very rapidly. And so it's not electrocapillarity, it's due to oxidation. And okay, this is not a perfect analogy, but if you wanted to lower the surface tension of a liquid, you would typically add soap. Hopefully all of you have done this today. If not, I probably will not shake your hand later. Anyway, so if you have like, say, oil and water that don't like each other, you can add soap and that goes to the interface and it lowers the tension from about 70 down to about 30. But in our case, we apply 1 volt, we deposit our surfactant, which is this oxide layer, and negative 1 volt, we can make it go away. So we can go huge changes in surface tension. And usually, well, okay, a couple things. So first, you might be thinking, wait a second. Didn't earlier he say that the oxide allows you to 3D print these kind of wacky shapes? Yes, that's Ga2O3, that's a solid oxide shell. But remember, we're doing these experiments in a bath that dissolves away the oxide constantly, so it actually allows it to flow. And not only that, but it actually, we've now gone and measured, it forms a different type of oxide. So they're not exactly the same. And usually, I think you said 72, a couple of you said, like, we're very shy and said 72. But most people don't know surface tension, so I'm gonna do something that's horrible and not very scientific. And I've got a bar graph here of tension of the liquid metal and water. But again, people don't really understand these. So let's just keep the numbers the same, and let's talk about numbers that you might appreciate. Mass, like when you go home and you stand on a scale. Okay, so water is 72, so that's like a dog in terms of gravitational force, like holding a dog in your lap. And when you put soap on the dog, it's like lowering it down to a 30-pound dog. It's still a dog, right? But it's a little bit smaller. In our case, the liquid metal is a polar bear, 600-pound polar bear, and with 1 volt, we're making it basically like a feather, but it's completely reversible. Soap is not reversible. You can go put soap in water, not so easy to get it out. Here, we can switch it. All right, these are, surface tension is a force per length. So I've got this kind of funny title here, change in voltage, about 1 volt can cause a huge change in tension, which is a change in force. This was done by Xiang, who's one of the best scientists I've ever met. And the idea here was to put 2 droplets of metal that have a surface tension, so they're squeezing like this, which should push up this weight. But then when you lower the surface tension, the weight squishes it down, and then when you switch the voltage, it goes back. So you can make little actuators. And in fact, he made a fish that's horrendously slow, but it's driven by surface tension. So the tension pulls, and it goes. Okay, so you can start to make these little muscles driven by surface tension. And if you were paying attention to my data, you may have noticed that this data starts to look like it might go down to 0. And you should be very mad at me. Why did I let my graduate student graduate without 1 more data point? That sounds so harsh. But do you realize all he had to do was turn the voltage, just go from here, this voltage, and just go to another voltage? Okay, so what happens if a liquid has no surface tension? You probably haven't experienced it, but what would it do? There's no penalty for it to increase its surface area. And remember, each one of these data points represents a shape of a droplet. It goes like from here to here to here to here. And so I'll show you what happens when we go to that 0, what looks like 0 surface tension. So when we go to that data point, this was done with Karen, this is looking top down. The 600-pound polar bear starts acting like it has absolutely 0 pounds. I guess that analogy doesn't hold. But anyway, so the electrode is right here, and you can see when these like little things break away, remember it's in sodium hydroxide, so whatever was on the surface dissolves and it just beads right up and floats away. Yeah, it's weird. So this has allowed us to do some really cool things. There's these things called Rayleigh instabilities, which you've all experienced if you've had like a drippy faucet or you have a hose or something like that where you had a stream of liquid. This has been known since the late 1800s. It's named after Lord Rayleigh. And every paper that you can find on this just discusses like how long does it take for the liquid stream to break up into droplets. Well, this is driven by surface tension, and of course you can make your stream go faster, which is what's happening in this diagram here, but eventually somewhere down further from the nozzle it will break up into droplets due to surface tension. But if we can make the surface tension to be 0 or close to 0, we can overcome this. So here we have a video where we pump liquid metal out of a nozzle that's 100 microns. That's the size of a human hair. And so we start applying a potential, 0.3, 0.4 volts. You see the droplets get smaller and smaller due to the smaller tension. And then at that same voltage that we see fractals, it comes out as a wire. Now, if you go a little bit too aggressive and you jack up the voltage, you end up with this crusty skin, and it looks like candle wax. And we wanted nothing to do with that, so we did not study it. But we said, okay, maybe this like stream that's coming down, we just need to give it more time and it would break up. So we found the tallest clear container we have in our lab, and it's going to strain your eyes here, but I'm going to point to it. That is our liquid metal wire that's going all the way down this tall container, and it's 100 microns in width. This is the 600 polar bear, 600-pound polar bear. You guys are hard to impress. So it goes all the way down to the bottom. And just to give you an idea, so this is mostly just an excuse to show a picture of my cute daughter. But anyway, it's not her braid that I want you to pay attention to. It's this little strand of hair that is sitting right there. That is 100 microns and about, she used to cry when we cut her hair, so at some point almost a meter long. Now we can cut her hair. But anyway, very, very high surface area for a liquid. And so last but not least, if you take this stream, you can demonstrate Lorentz force. Do you guys remember this? I always get confused, but I'm sure you remember your teachers doing this. So in our case, we have a wire, a metallic wire, and there's current going through it. Why is there current going through it? Because we're oxidizing the metal. Oxidation means you're taking electrons away from the metal. So there's electricity going, electrons are going this way, and we would call I going this way. So that's one of the axes. Then if we put a magnet behind it, we can generate a force. Normally, we don't care about Lorentz force because it's pretty small, but for a liquid, it does matter. Now, there's a second thing here called Lenz's law. You guys remember that? Wow. Of course you do. I had to look it up. So if you imagine this a magnet, this is north and this is south, the magnetic field lines kind of go like this. And so if you get close to the magnet surface, those field lines are parallel. But when you get close to the edge, they start to diverge. And so if you move a conductor through there, it actually will slow down as it gets close to those diverging field lines. And so I'm going to show you both of these effects in a very sort of stunning way. And by the way, this was done collaboratively, so I don't want to take too much credit, but I love showing this because it's so wild. So here is the liquid metal stream, and if you didn't know any better, you would say, oh, there's going to be droplets that come out of there. But I've already shown you, it's going to form a wire. Now I'm going to make the magnet disappear, so you're going to have to remember there's a magnet sitting behind the screen. So bye-bye magnet, but here comes the stream, hopefully. And there it goes. So Lorentz force whips it outwards. Lenz's law causes it to stop at the edge. You guys are hard to impress. Okay, go home tonight, turn on your faucet, and try to make something that's as long as a strand of hair. You won't be able to do it. But if you can, then try to get it to form a square shape in the middle of the hair. I don't know what this is good for, but it's cool. So here's another example where we put a couple magnets side by side. You can clearly see their shape. And then you say, well, why is there smoke coming? Well, that's the counter electrode is below, and that's producing hydrogen. So we're oxidizing the metal, we're reducing the water, and you can see the bubbles. All right, so, oh, this is fun. Do you guys know who this is? See, you guys work too much in the lab. This is a late night comedian, Seth Meyers. Okay, some of you know him. He was on Saturday Night Live. You heard of that show? Okay, I was worried. Anyway, this was a career high for me, so there's sound. Can I unmute? Okay, I'm just not going to talk while this plays. Maybe that will.
At North Carolina State University announced they discovered way to move and manipulate liquid metal with electricity. and Arnold Schwarzenegger has already been sent back in time to stop it.
So that's a Terminator. So yeah, so we got made fun of on late night TV, which was great. Okay, so I had one other thing I wanted to show you, but I think I got carried away. I'll show you one cool video, and then I'll take questions. But anyway, for what I've shown you so far is this, liquid metal. It's got lots of cool properties. This oxide layer is kind of the things we fixate on, controlling it, using it to print it, print the oxide, separate it from the metal, but also use it on the metal to control the shape of the metal. The other thing I was hoping to show you are these really tough ionogels. And, well, like I said, I think I bit off more than I could chew, but I'll just show you one cool video. We made these materials that we call glassy gels. So if you take a hydrogel, this is a polymer swollen with water. It's very soft, like a contact lens. If you make that same polymer but with no water, it's very hard. And this is like a dried out contact lens. But here we form what we call a glassy gel, which is a material that contains 60% liquid, just like the hydrogel, but it's using ionic liquid. And the ionic liquid makes the material very strong despite having containing a lot of liquid. And so it's the same polymer as the other two. It's just this one's very, very hard despite having the liquid. And the advantage of having the liquid is that it can make it conductive, and then it also makes it very stretchable. So sorry to tease you with that, but I know there was a couple people in the audience that wanted to see it, and I'm sorry I didn't budget my time better, but I'd rather have time for questions. So thanks for having me. And of course, I want to acknowledge the students that did the work. So please come visit us at NC State.
Questions? Don't be shy.
I would love to hear your question. Yay.
Okay, so just some technical question, but so when you print the liquid out and then you stack them, what make them connect together? Like if your surface is a solid, if I put two solid together, they won't connect, right? The second thing is that if you print the layer, what make that layer adhere to the substrate that you're printing on? Because you're printing different substrates. So I would imagine how do they connect would be different, or it's all one of a force in that stuff.
Yeah, those are great questions. So I get the first question all the time, and I've wanted to publish a paper because we sort of know, but we've never done it. So if you look at two droplets of liquid metal, which have the oxide on them, and you look at it with a high-speed camera, when they come together, you can actually see, I call it like a snowman. It looks like when you're building a snowman. When you build the snowman, the waist of the snowman, which is the skinny part here, you can actually see it expand very suddenly. And in fact, if you take a puddle of liquid metal that has the oxide on it, and you bring a droplet which has the oxide, and you bring them very slowly, as soon as they touch, it goes and it merges together. So why is that? Well, I think in the case of the snowman, there's at minimum, you're taking a round surface and you're trying to force it to be flat. And so the oxide has to break, the metal can combine, and then you get a liquid bridge between the two particles. So when you bring those together and you try to pull them apart, it's formed a new structure. Like it's like bubble gum. They're stuck together with the liquid. Now, what happened to the oxide that was at that interface? I don't know if it's very thin, right? So it probably just kind of crumbles up and goes away. Well, it doesn't go away, but it goes somewhere. Yeah. So it merges together. So basically that oxide layer is so thin and it's glass, right? So it's quite fragile that it just merges together. Now, for the printing, this is what's interesting about, another interesting thing about the oxide. If you don't have the oxide, the metal does not stick to hardly any surface other than other metals, just like the gold. It doesn't stick because it wants to form metallic bonds. So like if I had it on this table with no oxide, it would just roll around just like mercury. But with the oxide, it sticks to just about everything. And anybody that works with this material will know, it's like wet paint. You get it on this table, it's like you try to wipe it off, it just smears and it's really stuck to the table. So the only surfaces that it doesn't stick to are rough surfaces. And why is that? It's kind of like what's called Cassie-Baxter effect, where you've got so you have basically a rough surface, And then imagine this as roughness on your surface. When you bring down the oxide layer, it can't like penetrate all the roughness, and so it actually doesn't stick very well. It still sticks a little bit, but not very well. So this printing thing that we do, it doesn't work on rough surfaces. But if you drag it across a smooth surface, the oxide layer essentially facilitates the adhesion. And like you said, normally when we take two solids like this, they don't stick because they can't make very good contact. But because the oxide layer is only 3 nanometers, it's very compliant. And so it will like just make really intimate contact, and then it sticks because the oxide can make hydrogen bonds, it can make van der Waals forces, it can do all these things that the metal is not so good at. So, and actually using that electrochemical trick, you can switch the adhesion. So we've made robots that can stick to things underwater, like with the oxide, without the oxide. Yeah. So great questions. Thanks.
Thank you so much.
Thanks. You already got an A++, so I'm a little scared of what question you're going to ask.
It's actually a continuation on the printing part. So you mentioned the indium gallium is in a particular stoichiometry in your eutectic. Is the oxide also eutectic of the two metals in the sense that does it have a mixture of those? And if there's a preferential oxidation of one metal over the other, does the stoichiometry of the droplet change as you print?
Oh, great questions. So the metal that we print, so first of all, you can print pure gallium. You just melt it and print it, no problem. And then that forms, of course, gallium oxide. With the alloy that we print, eutectic gallium indium, it's about 25% indium. And it turns out it's actually a little bit complicated. So if you go into a vacuum environment where there's no oxygen and you remove the oxide, indium actually goes to the surface because it has a lower surface energy. So indium prefers to be at the surface. However, gallium is much more reactive than indium. So its delta G of reaction is more negative. And so the oxide that you get is almost pure gallium oxide. So even though it's 25% indium, there's almost no indium. I mean, there's a little bit, but it's almost undetectable. And so your point is a good one. If you just took this and you started dragging it across the surface, and you print over miles and miles, at some point you're going to consume all the gallium, and at that point you would get what we would call like off eutectic. It's not at the eutectic point anymore, and so you can start crystallizing the indium and start crashing out. So, but that requires a lot of surface area because this layer is only 3 nanometers thick. So you would have to print quite a bit. We don't actually see that in practice being a problem. But if it was a problem, we would just use gallium. Now, if you add aluminum is even more reactive than gallium. So you could have indium, gallium, and aluminum all in your alloy, and then the surface becomes aluminum oxide. And that's very cool because in that case, what we showed, we only added I think it was 1% or 0.1%. It's a very small amount of aluminum, and that goes to the surface. So we haven't done it, but some people have made other types of oxides by controlling the composition of the alloy. Yeah, so it's kind of cool. Yeah.
If I may ask one question, this was a fascinating talk, and I was wondering, this might be a crazy question because you have a problem with the electricity, with the electric field, with the water, etc. Have you ever thought about, for example, using other solvents that are conducting but don't electrolyze? Just out of curiosity.
Yeah, when we first tried, I think we got our hands on some ionic liquid, which has a bigger stability window where it won't start undergoing reactions. I don't remember what happened. We sort of ended up abandoning that. But you have to, in order for the tension of the gallium to lower, for it to start spreading, you have to have oxidation occurring on the gallium surface, which means at the counter electrode, you have to have reduction. And the trick that we've tried to do was to, instead of reducing water, which produces bubbles, reduce something else, like a metal salt or something like that. But it's tricky because if you add a metal salt, it can actually start undergoing redox reactions with the gallium itself. So yeah, so it's just complicated. There might be if you pick the right metal where you could get it to deposit on the counter electrode, but not on the gallium. But anyway, yeah, it's complicated.
Thank you. Any other questions? Well,
Please.
yes, well, let's thank Mike again. Thank you.
Thank you.